So I want to talk, just hit some of the other aspects of this particular story, and I'll just say right up front that I prefer the second model, the traditional cryovolcanic flow, which is why it says it up there. So, but let me back up and just say what a remarkable thing it is that we had to go all the way to Pluto to find the ammonia that John Lewis predicted would be so abundant in the outer solar system. Of course, we didn't find it, that is the New Horizons team. It was discovered from the ground. It was the first body where more or less definitive spectra were taken. And there's a whole list starting with Mike Brown and Wendy Calvin's work back in the last millennium. Okay, but this is right here I just show a particularly nice set of spectra done by Jason Cook a few years later, which shows this particular feature at 2.21 microns, which of course they identified, or in a sense re-identified, as ammonia in some form on Charon. And this has been seen at leading, trailing, sub-Pluto, anti-Pluto hemisphere, etc. Now, that's from the ground. When you go up there, what you actually find that the ammonia is everywhere, and what you see are a set of spectra here where there are in fact two features, one at 2.21 and one at 2.01. When you see them both, you have a much higher confidence that you really are looking at ammonia. You don't really know whether it's monohydrate, dihydrate, or even pure ammonia, but that's pretty much what it is. And this particular figure on the left is from an abstract of Jason Cook's Lunar Science abstract, in which the dark spots are particularly ammonia rich, and they're numbered, and they just show the different things. And you can see that, I think you can see by eye the dip at 2.21. Now, of course, there's more to the story, right? So there's been a lot of work. In fact, there's a very recent paper published by Delaware et al. Okay, this is from the composition part of the New Horizons team, and they're looking at both bands, the 2.21 and the 2.01, and the sort of the blue and the teal show you where the band depths are concentrated, and they don't exactly match, but they're all over the place. And we know that Charon's covered with craters, so in fact there's ammonia in some form pretty much all over the surface, some of which, like Ross said, is associated with fresh craters. Just going further, they took the spectra and then binned them, or actually sort of clustered them statistically as to like which are the spectra that are most like each other. And one particular cluster, which they called cluster 1, is more concentrated in Vulcan, Planitia, if you like, in the south, and it's also around this particular crater. And it was actually modeled with radiative transfer modeling. And I want to make a point that has escaped because it overturns a little bit about what the received wisdom in the field has been. The ammonia in cluster 1 is actually not trivially small. In fact, because of that 2.01 micron band, this particular model actually has nominally 40% ammonia. Now, what they really mean is not 40% pure ammonia, 40% ammonia monohydrate, because that's the optical constants that they had. So in the places on Charon that are indicated by this blue, there's actually substantial ammonia in the near surface. And so you might ask, why has it been so difficult to detect all these years? Well, one reason is, in fact, that ammonia is not, in fact, a large bulk component of any body we really know of, any solid body. Comets only have about 1% ammonia compared to water. So, and then this has to do with kinetic inhibition and molecular cloud composition and this sort of business. And so what John Lewis was talking about was equilibrium solar composition, because there's a lot of nitrogen in the universe. It also turns out that ammonia is simply harder to see because it is, in fact, part of this complex with water molecules, hydrogen bonded. Mostly what you see are these big water ice bands with these small features. And it's already been mentioned that ammonia is, in fact, and you can show it in the laboratory, it's unstable under UV and charged particle bombardment. So we don't expect it to last forever. But then the implication is that if we see it on Charon's surface, certainly in this kind of abundance, it must be refreshed on some appropriate timescale. Just because you see ammonia doesn't mean there's active cryovolcanism, but it does mean that there must be ammonia accessible to the surface, so that, what I think anyway, is that some regolith overturn continues to bring up fresh ammonia that then gets sputtered and UV photolyzed away. Okay, so let's talk about why I think, or why Ross and I think, that in fact this really is a cryovolcanic plain, like the lunar mare. You know, when you go to the lunar mare, you can actually see the different lava units because they have different albedos, different colors. This is determined by the amount of potassium, not titanium, in the basalts. If you have a young enough surface and you have high enough resolution, as we certainly did with the moon, you can actually see individual lava flows. You're absolutely sure what's going on. You can even see part of the plumbing system, what carries in this case, the fluid basalt from hundreds of kilometers across the mare surface. You can even see late stage eruptions that in the youngest parts of the mare, like this one was the Mare's famous Mare's Hills. Here's another one, the Mons Rumker. Very interesting, must be much more silicic constructions. What you do not see when you look across the moon is where all the lava that is feeding those rills is coming out of. And that's because these are flood basalts, okay? So they come in, the amount erupted is large, the effusion rate is large, and the plumbing system must come from below in the fractures or dikes that were talked about earlier by Sarah, okay? And of course, we see this on the Earth. We see how it operates in the Columbia River basalts. We see it in the Precambrian terrains where the basalts aren't even there, but you can still see the planed off roots of these systems. So on the moon, this must be what's going on. And in fact, we even have some very tantalizing evidence that this is really how it's working. The more recent work from the incredible GRAIL gravity mission, you take the gravity gradient, and Jeffrey Andeshana and the team interpret these linear structures in the near side of the moon to actually be the signature of frozen basalt-filled dikes that ultimately fed Oceanus Procellarum and many of the other near side basins. So the fact that, as Ross and I used to argue about, the fact that we can go to Charon and not see the vents, at least we're not sure we can see the vents, doesn't mean that they can't be cryovolcanic. Anyway, on to Charon. You've seen some of this stuff already. The extent of Vulcan plenum that we know of is given here. This is in the encounter hemisphere where we have good resolution. We can't really tell so much of what's going on the other rest of Charon because of either polar night or because our resolution isn't as good. Here's a topography that Ross referenced before, and by the way, there will soon be in Icarus a fabulous paper with an incredible wealth of topographic data led by Paul Schenk. As Ross alluded, the northern part of Charon is extremely tectonically disrupted. Vast blocks separated by troughs or graben, which fit into the tectonic pattern where we come up to the edge of the plane where things now drop down to this plane, and this is the topo, and this is the actual image. I'm just moving along, and I just make the point. Here's a topographic profile, the same one that's in the abstract, and this is an expanded black and white scale, but you do drop down onto Vulcan, and it's not a planum anymore, and so hopefully we'll get the IAU to approve the name Planitia. So this is the topographic profile, but you can look at that in the abstract. So in terms of the details of the kinds of things you've seen, there are lots of craters, so it's not exactly a young surface, but there are subtle variations in certain regions, and you've already been introduced and had a discussion of the linear rill-like features and the more sinuous rill, or at least flow-looking lobate features. There's Kubrick Mons in its moat. Here, very much close up are, actually let me back up. So I want to look in this region right here. Let's do that. So this is one of the more interesting regions to me. There's more cratered regions. These are the mountains, but don't just look at the mountains. Look at this interesting, smoother patch. There's a fine set of fissures, if you like, on the surface here, and then it stops here. And then there's a it looks to be almost like a pancake-like deposit or construction with individual blobs on it, which remind you of the kinds of volcanism we see on the silicate worlds. And when we look at the topo, and this actually comes from the science paper led by Jeff Moore, that this smoother plane here is in fact lower than the sort of the more rilled plane right here, and then this thing in fact really is higher standing than them all, and it has it seems hardly any evidence of cratering. So there's evidence for some multi-stage cryomagmatic activity, at least I would argue that. There's Kubrick again. This again gets to this point that Louise was saying, well, what does this really look like? I think it actually looks like it's embayed but not entirely enclosed. Like the things, and here is this strange, is it a drainage? What's going on? It's very hard to tell. If we go a little bit, if we go to a different part of the Planitia, to the other edge, to the southwestern part, these are those strange, but again, they're actually reminiscent of the patterns you see on some of the smoother terrains on the moon aerial, and they do give the impression of being related to flow, but the question is, are they the merging of flow fronts, or is this the source of the material? And here's another, where is it? It's hiding. There, isn't this sort of little dimple here? It seems to be, is stuff draining in or is stuff coming out and then collapsing? I don't actually know. And I'll just point out that to the western edge here, there are these bounding moats, and I think you could easily have, even if they don't, as Ross argues, come up and freeze before getting to the edge, they could actually be flat, and then the weight of the rest of the crust could cause a bit of downsagging at the edge. Actually, I shouldn't have, this is actually a close-up picture. It's sort of a little bit out of order, I guess. So this is this interesting sort of constructional-like, or at least pancake-like feature, and it is topographically higher. It's cut by this rill, and then this is a much smoother one. You can actually see the actual differences in crater density now between this particular subunit and, let's say, this unit over here. And that comes again. Does this make any sense? And the actual answer is yes. I don't have a lot of time to talk about these kind of things. There is enough energy from radioactive decay to melt at least part of Charon's mantle. And this is from a paper by a student of Francis Nimmo, which we worked together with on Carter Barrison. And this is actually for Pluto on Charon. But if you look at the bottom one, this is just one model. And you know, when you do these sort of models, you can pick your conductivities, you try to be sensible, or you try to vary them within ranges and see what you get. This is sort of a characteristic calculation, starting with a cold but differentiated world and simply asking what happens. And in Charon's case, you get an ocean and the ocean freezes. And the key here is actually this ocean has no ammonia in it. This is an ammonia-free model. You can see the temperature profiles here. If you can imagine putting in that 1% ammonia, okay, then you will probably get a larger and longer lasting ocean, but it will probably still all freeze solid by the end of, well, by today. If you ask the question, if I have 1% ammonia, then you're going to get 3% ammonia dihydrate, okay? And you add that to Charon's bulk and you say, how much, if you erupted it all to the surface, how much do you get? The entire surface could be covered over with 4 kilometers, okay, of ammonia dihydrate. So there's certainly more than enough to provide the material that floods Vulcan Planitia, because Vulcan Planitia, that which we can see, is only 10% of the surface area of Charon. So that works out. So, and you know, I think, and this is just due to radiogenic heating, and I think, and the timing is probably appropriate. You see that the freezing of the ocean is an early event in solar system history, billions of years ago. Ross mentioned this one thing, so I'm just going to mention it again because I want people to think about this. I am really puzzled by this strange textured terrain on Charon. Like, you know, on Pluto we're fine because we have ammonia and we have nitrogen, and this stuff can do all sorts of crazy stuff by sublimation. There's no evidence for these kind of materials. Charon is darker and warmer. These super volatile ices are not stable. Could this be the signature of sublimation of ammonia itself, or some sort of sputtering process? Don't know. This is, and then this is, we do it in map projection, so you can actually see it a little bit more clearly. It's a very interesting pattern. It almost seems to have a characteristic scale. Okay, so what is it? Is it a primary texture like lava? I don't know. Could they be secondaries, billions of little secondaries from somewhere? We don't see the craters for that. Maybe there's a lot of small impactors out there that at the limited resolution, remember this is right at the terminator at the best images we see on Charon. Or really is it just due to some sort of sublimation or radiolysis instability? I don't know the answer, but it's one of the more interesting aspects of this business. I will say, this is very complicated, but let me just say this is an R plot. Everybody loves R plots, I know, in this audience. Okay, this is work of Kelsey that's under review. Okay, so this is the measurement of the crater size frequency distributions on Vulcan Planum, and basically comparing it to a model that we published a couple of years ago on how fast craters should accumulate on Charon. We kind of estimate that even Vulcan Planum is, like the lunar mare, really pushing it, on the order of 4 billion years. But of course, there are uncertainties in the cratering, not in the cratering record, but in the mechanics of cratering. It's not totally terrible, but it could be 4.4, it could be 3.5, maybe even 3. We don't really know, but it's definitely old. One thing that we really see, which is just amazing, is that when you get to crater sizes less than, let's say, 10 kilometers, it takes a real change. There's a real change in the power law slope. So you will have a deficit, a dearth of very small craters. And so if I were to just back up for a second, one of the interesting things about looking at the surface of Charon that's different from the moon is like when you zoom in on the moon, like Ranger did long ago, it's self-similar. There's just craters, 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 and it's all saturated. That's not true of Charon. You get down to small enough sizes, you're seeing some sort of primary surface, okay? Maybe there's small-scale churning to get that ammonia out, but it's not like the lunar mare, so it's on that level. And so that's just an interesting part. So just to sum up, just to end up, it's a type example, I think, of cryovolcanic flood volcanism in the outer solar system, and in fact, it gives extra extra weight to previous interpretations that were always tentative that these kind of things might actually occur. You look at Ariel around Uranus, it's like disrupted blocks, smooth materials, sinuous troughs. I mean, it all fits together, and you say, well, does Ariel actually have any evidence for ammonia? This is a figure from a paper that's just gone into press in Icarus, that again led by Jason Cook, in which he took all of the spectra from a whole bunch of bodies where people have suspected ammonia. When you suspect ammonia, you're not sure, but when you go to Charon and you say it really is ammonia, then you go back and you look at the older spectra and you say, well, maybe we did see it. Here's Ariel. So there's sort of a dip at 2.21. Miranda might even be better. And I won't go through them all. So the ammonia is probably actually out there, and probably in amounts that we don't truly appreciate. And so, given that Lynette is standing up, I will just end up with one of Paul Schenk's fabulous movies. So this is Over the Textured Terrain, and we'll move across Clark Montes, across the my favorite volcanic region, into this sort of smooth patch here, and then up to the edge of, I guess it's Serenity Chasma. Thank you.
All right, is there one very quick question for Bill while we go through getting the next talk up?
Well, there's Jeffrey right there.
Very quick. Early in your talk, when you were showing the map of ammonia distribution, you said ammonia monohydrate. Did you mean that, or did you mean ammonia dihydrate?
No, I meant that the spectral analysis used the optical constants of monohydrate because that's what they had.
Okay.
So that's the interpretation, that 40% of the pixels that are identified in cluster 1 are ammonia monohydrate. Depends on those optical constants being right. And this kind of work needs to be redone with the dihydrate, and maybe even as Julie was indicating earlier, it could also be ammonium chloride. In that Cook paper, by the way, it's really about the small satellites of Pluto, which also have the ammonia feature, and they get a very excellent fit to ammonia chloride, but then say, I didn't write the paper, so then say, but we don't think this is the answer. but maybe it is.